All right, this is matrix approximation, video 3. So the goal of this is to understand what the singular values mean and to summarize. So in order to do that, we need a couple of definitions, or one definition applied to two situations. So given a collection of vectors, we'll say the variance of that collection. This is just the sum of the squares of the lengths of the vectors. And so coupled with that, if we have a matrix which we can think about as a collection of vectors, so given a matrix A, we'll say the variance of A, which we'll denote by the magnitude of A squared. This is just the variance of the columns, the set of columns. So just so we have a visual idea, right, this is the sum of the squares of the lengths. So basically the longer the vectors are, the greater the variance is. So if you have a collection of vectors, all of which are small, like this is low variance. If you have vectors maybe which are large, they don't all have to be large, but if a bunch of them are large, this is high variance. So variance is a way of looking at the spread of the data, and we've been using this term spread a lot. This is a way of sort of nailing down precisely what the term spread means. So to see how this connects to all the single values, we're going to take a trip back to a calculation. Let's return this calculation. We did a calculation before of what the columns of A looked like, right? This came from this A equals U sigma V transpose. So we saw the following. Let me pause and fill this in. All right, so take a look at this. We saw this earlier, which is why I didn't want to spend too much time going through it. This just emerges from the calculation A equals U sigma V transpose if you just dig into the way that we multiply matrices, right? So for a second, let me focus just on the first of these. So if I take the norm of this, just both sides, the UIs are perpendicular. So what I'm actually going to do is take the norm squared of both sides, and then the Pythagorean theorem kicks in because they're perpendicular. So what we get is A1 squared is the equal to is the sum of all these squares. Let me just write dot dot dot. It's just the very first line. Now, so this is because the UIs are all perpendicular to one another. So now what happens when we do this, of course, is the S's and the V's, these are just scalars. So they come out and get squared. But the norm of U1 is 1 because the U's are unit vectors. So this just turns into, let me write the second term this time. This goes all the way to the end. These are because all the norms of the UIs are 1. So again, this is just for the very first row right here. So let's repeat this for all rows. So when we do this, I'm just going to write dot, 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 and the very last one, so we'll get a sub n squared is s sub 1 v sub n1, those are squared, plus s sub 2 v sub n2, those are squared, all the way up to and including s sub k squared v sub n k squared. That's all the other columns, same idea. And then what we're going to do is we're going to add all of these rows. So when we do that, on the left-hand side, we just get the variance of A squared, well, yeah, the variance of A, which we'll denote as the norm of A squared. On the right-hand side, it's a little sneakier. So take a look at just, say, the first bunch. So all of these have an S1 squared in common. So those factor out, and then we get the sum of the squares of the V's. But that just gives us the norm of V1, right? So V11, V21, V31, that is the first column of the V's. That is the vector V. So that V is also a unit vector. So this just comes out to be S1 squared. The second one is S2 squared. The last one is SK squared. So what this says is that the total variance of the data is the sum of the squares of the singular values. But moreover, it tells us one more thing. It tells us that the variance in each direction is that singular value squared. So the variance in direction ui is si squared. So all of this is sort of all the good meaty stuff now. We have everything. We have a visual understanding. We have some measurements of what these singular values mean. So what I'll do next is I'll clear the screen. I'll give a really comprehensive summary of everything that we've got, and then we'll go back to the original example and we'll point some things out on this example so we can see how it's all working, so we really understand what these terms like variance in a certain direction means visually on the picture. So let me clear the screen and do this summary. So I think actually this is number 4. Doesn't really matter. So this is what we've got. This is with A equals U sigma V transpose. So first thing that we saw originally way back is the U sub i's give the directions of spread. Now, A and B could potentially be coupled together, but I'm going to keep them separate. So assuming we've ordered everything in a nice order, you know, the sigmas are in decreasing order, what we'll say is the order U1, U2, etc. This sort of gives the priority. Or let's say the order in which the data is spread from most to least. Now, to concrete that, we can be more specific. We can say that the variance in direction ui is si squared. Then we have the total variance. is the sum of all the s's. Let's say sum of s sub j squared over all the possible singular values. So that then gets us to something interesting, because it's generally often not the actual variance that matters, it's the proportion of variance, because if you have a very small overall variance, then it's the proportion that matters, right? So we could say the proportion of variance in direction ui is just, not sigma, rather, si squared divided by the sum, by the total variance. And then last, for example, we can simplify the data, right? We can remove a direction of data. By, let's say, changing sigma, right? So we pick the direction we want to eliminate. We replace the s sub I by 0 to get, we'll call it sigma prime, and then we construct, if you like, is maybe a better word, use sigma prime v transpose. That'll sort of simplify the data. And when we do so, of course, if the variance is small, in other words, if the SI we remove is small, then the difference between the two matrices, between A and A prime, is small. Now, by difference, we can literally mean the variance between them, if you like this. Right, but that will be small, because the difference between the vectors in each of those is small. So let's take a trip back. What I'm going to do is I'm going to pause for a second. I'm going to draw in the original picture of the original data, and then we can draw some pictures on it. We can sort of label some values, if you like, to understand exactly what we've measured in all of this. Alright, so this is the original graph, and below it I have the original matrix with its original singular value decomposition. I've plotted the U's, we've got the 4 points, everything's good. So I want to point out what we've got in terms of what we just said, right? So let's look at these singular values, the 5.855 and 1.312. So if we take those and we square them and we add them, that's the total variance. That's 5.855. There's a little bit of approximation going on here, but this turns out to be 36. That's the total variance. Now, if we look in each of the directions, so for example, if we look in the U1 direction, so let's focus on the rightmost point on the screen. So that has like a variance in this direction. This is the variance in the U1 direction. This is the variance in the U2 direction. Now, each point has that same feature. So for the point that's above it and to the left, we've got variance in the U1 direction, variance in the U2 direction. For the other one, we've got variance in the U1 direction and the U2 direction, U1 and U2. So what that means is, if we look at those lengths, right? So for example, I possibly should have done these in different colors. That's right. Let's just emphasize this for now. Let's just do these ones right here, these intense ones. This is the variance in the U1 direction, U1 direction, U1 direction, U1 direction. So if we take that total variance, so the variance in the U1 direction, that's 5.855 squared. In other words, literally, if you take the sum of the squares of those distances, this is what you'll get. You'll get that value. That value is 34.28. Now, the proportion in the direction is that 34.28 divided by 36. That's 95.22%. Whereas if we look at the variance in the U2 direction, that's 1.312 squared, that's 1.72, and the proportion is 1.72 over 36, which is 4.78%. So what that tells us is the majority of the variance, like percentage-wise, proportion-wise, if you like, is in the U1 direction. And the smallest amount of variance is in the U2 direction. We have numbers to represent that, right? 95.22 and 4.78 to give proportions. If you want actual variance, you've got 34.28 and 1.72. So that's a really, really simple summary. Really simple two-dimensional example. So what I'll do is I'll stop the video now, and then I'm going to do another video where we work through another example where we make some choices about removing values and see what kind of analysis we can do there. So that's the end of this one.